Chapter 11, Vectors. To start with, we need to have a basic understanding of what a vector is. Rather than explain this myself, here's a short introduction to a TED video by David Hoon, and this will give you a brief overview.
Physicists, air traffic controllers, and video game creators all have at least one thing in common: vectors. What exactly are they, and why do they matter? To answer, we first need to understand scalars. A scalar is a quantity with magnitude. It tells us how much of something there is. The distance between you and a bench, and the volume and temperature of the beverage in your cup are all described by scalars. Vector quantities also have a magnitude, plus an extra piece of information: direction. To navigate to your bench, you need to know how far away it is and in what direction, not just the distance, but the displacement. What makes vectors special and useful in all sorts of fields is that they don't change based on perspective, but remain invariant to the coordinate system. What does that mean? Let's say you and a friend are moving your tent. You stand on opposite sides, so you're facing in opposite directions. Your friend moves 2 steps to the right and 3 steps forward, while you move 2 steps to the left and 3 steps back. But even though it seems like you're moving differently, you both end up moving the same distance in the same direction, following the same vector. No matter which way you face or what coordinate system you place over the campground, the vector doesn't change.
So, back to our work in Chapter 11. First, have a quick read through the objectives for the chapter, then I'll scroll down so you can attempt the prior knowledge check. These are really important for you to be able to start the chapter with enough prior knowledge to be able to understand the initial concepts and ideas that we're going to cover. I'm happy to go through the prior knowledge questions in the lesson if and when you need to. Just ask any questions as we're going. So, as we've already heard, a vector has both magnitude and direction. For example, 5 meters north or 500 kilometers on a bearing of 060. We can represent a vector using a directed line segment, as shown here. We can see that these are vectors as they have magnitude, the length of the line, and direction, the way that it's pointing. We call the first vector PQ, as the arrow is taking us from P to Q. The second vector would be QP, as the arrow is now taking us in the other direction. So P to Q and QP. Instead of using the letters at each end of the vectors, we can instead give the vector a small lowercase letter to represent it. It's written with a line underneath to indicate that it's a vector. In textbooks, however, it will just be displayed in bold. Consider these two vectors, PQ and RS. As they're both the same length and going in the same direction, they're parallel, we know that PQ must equal RS. Here we can see that AB equals negative BA, as the line segment AB is equal in length and parallel, but in the opposite direction to PA. Just have a moment to make sure you understand this. When working with vectors of this type, I try to think of them as roads that have a particular direction of travel. We can travel back along them, but we are going against the normal flow and must take this into account when writing out our journey. Now we're going to look at the triangle law for vector addition. So, AB plus BC equals AC. AB plus BC equals AC. If we think of these as streets that we can travel down, we could either go from A to B, then from B to C, or we can just go straight from A to C and we end up in the same place, the same distance away. Therefore, AB plus BC equals AC. We call the sum of two or more vectors the resultant. Example 1. This basic example shows you how to combine three vectors by adding them. First, travel along vector A, then along vector B, finally along vector C. Vector A plus B plus C can be represented by drawing a vector directly from A to C. The resultant is then the vector that is created from the start of A to the end of C. Subtracting vectors. Subtracting a vector is the same as travelling backwards along the positant equivalent vector. For instance, if we have these two vectors, A and B, and we want to subtract B from A, we reverse the direction of B and then add. So, here's A, and B should take us off in that direction, but because we're doing A subtract B, we end up coming back down. Adding the vectors PQ and QP gives a zero vector. PQ plus QP. That means we end up exactly where we started. Multiplying vectors. We can multiply a vector by a scalar, some number, and we then have a different vector that is of greater length but is in the same direction. For example, here's vector A. If we multiply this by 3, we end up with a vector of magnitude 3 times as big, but still in the same direction. This idea of scalars will be key later when we delve further into the topic. We can also multiply by a negative scalar, which may change the direction of the vector, but is still parallel to the original. B minus 2b minus a half b. Example 2. In this example, we're going to find routes that take us from one point to another, where we don't already have a vector representing that particular pathway. Let's look at these one by one. Firstly, we're at P and we want to get to S. Now we don't have a direct route, so instead we have to go round the houses. We need to find routes that we do have vectors for. So we could start at P and go up to Q, and then once we've got to Q we can come back down to S. That's why PS, to get from P to S, is PQ plus QS. Well, P to Q is negative A, and Q to S is C. And instead of writing it as negative A plus C, we write it as C minus A. For R to P, I'm at R, and I need to get all the way across here to P. Again, I'm going to go along the routes that I have vectors available for. So I'm going to go up to Q and then down to P. So I'm going to go negative B and then plus A, because I'm going back along B and then following the direction of A. Again, we'll write it as A minus B. Part C is to get from P to T. I'm at P, I need to get to T. I can't go direct, so I'm going to go back along A, then down B, then down D. So, minus A plus B plus D. What they've done here is they've said that it's P to R, which we already know, and then R to T, which is along D. P to R we know because RP was A minus B. So P to R will be B minus A. Then add D and we have PT. Finally, T to S. Now in order to get from T to S, we're going to go from T to R and then R to S. T to R is easy, that's negative D, back along D. And then RS we're going to take as being RQ plus QS. So that is negative B plus C. We end up with negative D plus negative B plus C, or C minus B minus D. And that takes us from T to S. The parallelogram law for vector addition. Because a parallelogram has two pairs of parallel sides, if we're told that we're working with a parallelogram, we can use this to quickly work out vectors that aren't given. In example 3, we're told that ABCD is a parallelogram. AB equals A, AD equals B, and we're looking to find A to C. In order to get from A to C, we simply go along A and then along B. So, AC equals AB plus BC, well BC equals AD, which is vector B, so that's going to make life easy. AC is A plus B. Demonstrating that vectors are parallel. Two vectors are parallel if we can show that they are both the same vector being multiplied by different scalars. For example, 3 lots of 2a plus b must be parallel to 5 lots of 2a plus b because they're both going in the direction 2a plus b. They're just of different magnitudes. So for example 4, what we're going to do is we're going to factorise each of these. Firstly, 2 lots of 3a plus 4b for 6a plus 8b, and then 3 lots of 3a plus 4b for 9a plus 12b, and as 3a plus 4b is in both, they're just being multiplied by a different scalar, they must be parallel. If I was looking to demonstrate this, I would write 6a plus 8b equals 2 lots of 3a plus 4b, and 9a plus 12b equals 3 lots of 3a plus 4b. Therefore, they are parallel. For example 5, we've got a triangle ABC. We're told that AB equals A, AC equals B, and we're told that Q lies 3 to 2 dividing AC. So that means that this A to Q is 3/5 of the distance and Q to C is 2/5 of the distance. So, to write these in terms of A and B, B to C is going to be B to A plus A to C. Well, B to A is negative A plus A to C, which is B. So that is B minus A. For part B, A to P, well, P is the midpoint of AB, so that's just going to be a half A. For part C, A to Q, well, A to Q is 3/5 of B. And then finally for D, we've got to go from P to Q. Now we could start from scratch, but actually we can think of this as being P to A plus A to Q. I know that P to A is going to be the negative of A to P, so that's going to be minus a half A, plus A to Q, which we've just worked out as 3/5 B. So we're left with 3/5 B minus a half A. Now, I would like you to work your way through exercise 11A. There's no substitute for practice. So start at the beginning. It's really straightforward to start with, but you'll build up your skills gradually. Work through exercise 11A, and if you've got any questions, let me know.